Okay, so if you remember for power switch, we said that if we have power switch like this, so it depends on the load that we have and why we use this power switch. We have current and voltage applied on this switch, right? We have currents flowing in the switch when we turn on this switch, and voltage applied or voltage across this switch or the voltage stress across this switch when we switch off this switch or when we make this switch open circuit. Now the issue is when we give order to open the switch or to make the switch turned on or conducting, what happens for the voltage and current? Look at this voltage here. The voltage will start flowing, will start falling to zero gradually, and the current will start flowing within the circuit gradually, right? So as we said, this transition makes what we call power loss, right? Because if you multiply the voltage and the current here, you will find that we have a power loss voltage times the current. Similarly, we have the same problem happens when we turn off the switch. The current will fall down to zero and the voltage will start increasing, and again we have power loss here according to this process. Okay, that is what we call hard switching. Hard switching happens when we send the switching order if we have non-zero or non-zero current or non-zero voltage. Okay, so at this moment we have non-zero voltage, non-zero current here, so here we have hard switching. So we have power loss that can be occurred when we switch off or switch on the switches. Okay, why do we need this actually? Actually, we don't need this. We cannot change it easily because this happens according to the circuit behavior. Okay, so it depends on the circuit itself, the converter itself, the load on the converter, okay, the position of the switch. Some converters we cannot change anything on these switches, okay. The order, once we send the signal to the switch, what happens is the voltage will fall down, the current will flow in the circuit, so nothing will be changed. We have switching losses. Okay, now at some circumstances we can easily or we can make some adjustment in the circuit to make sure that this area, the overlapping area, is as small as possible. Okay, like if you look at this point here, sometimes we'll be able to move the current or the voltage to be like the overlapping to be minimum, and at this point we can reduce the switching losses to be also minimum. Okay, the overlap between these voltage and current while we're switching to be minimum. Or sometimes if we apply like resonant circuits, okay, if we take advantage of resonant converters, we can fully switch at zero current or at zero voltage switching. Okay, and that's what we call soft switching. Okay, so if we manage to make switching at zero voltage or at zero current, then this is a soft switching. If we manage to move this slope to be minimum, to make the overlap to be minimum between the voltage and the current on the switch, then what happens? What we call this one like semi-soft switching. Okay, so I want you to look at the switching behavior here. The switching action happens here. So once look at the voltage and the current here. Now for this one here, the voltage is not zero, so we can say that this is a not zero voltage switching. But if you look at voltage here, the voltage is zero first, then we apply the switching action, so we can say that this is a zero voltage switching. Okay, here is the same thing. If you look at this point, this is a zero voltage switching. Now for this point here, if we apply like this one should be shifted here, this one should be here, the switching should be at this point. So the switching happens at zero current switching. We can say this is zero current switching, and so on and so forth. If we manage to get zero voltage switching or zero current switching, then this is what we call the soft switching. Now within the converter, there are three main types of zero voltage and zero current switching, which depends on the where this soft switching happens. If we manage to get the zero voltage switching or the soft switching at the switch itself, so if you add, for example, capacitor and inductor, or what we call the resonant circuit on the transistor itself, so this is what we call the resonant switch converter. Sometimes we make our circuit and we make sure that the resonant behavior occurs on the load side, so this is what we call the load resonant converter. And sometimes for the inverter, for example, the resonance occurs on the input side or in the DC link capacitor. So this can be called the resonant DC link converter. Okay, so the question is, now we have switching losses, okay? These switching losses consume loads of power. We do our best to minimize these switchings by applying soft switching, to make sure that we have zero voltage switching or zero current switching. Now, why we need resonant converters? Why we care about the resonant circuits? By definition, or if we come back to the basics of resonant converters, you'll find that the resonant circuit is a combination of capacitor, inductor, and resistor, and the equivalent of this network can act as a resistive circuit. The capacitor and the inductor try to cancel each other. By this way, we'll be able to extract the maximum power from our network and then increase the maximum power transfer from the circuit. If we apply this one on the switching side, you'll find that we have zero voltage switching and zero current switching. So we have like the maximum efficiency, right? So that's why like resonant circuits in power converters are very important. We cannot differentiate between the resonant converters and soft switching, hard switching, because they are very linked to each other. Okay, now let's look at the resonant networks or the resonant circuits. Here we have a few types of resonant networks. The combination of these two, capacitor and inductor, can cancel the effect of each other. Okay, for example, if we look at the series resonant network or the series resonant circuit here, the resonance happens when we manage to make sure that the capacitor and the inductor cancel each other. If we manage to tune the capacitor and the inductor value at certain values, these values can make as a short circuit. If we manage to get a short circuit from this network, so this is as we have a resistive load only. Okay, and then we can get the maximum power. Similarly here, for the parallel resonant network, if we manage to make sure that the capacitor and the inductor here act as open circuit, then as if we have only a resistive load here, and we manage to get the maximum current. So all the current from the input is going to the output, right? So at this point, we make sure that we have the maximum power that can be extracted from the input to the output, okay? So why we need this in power converters? If you look at the transformers, for example, if you remember, we said we have loads of parasitic elements in the transformer, and these parasitic elements like capacitors, inductors, which are not actual passive elements, when we increase the frequency, the value of these capacitors, inductors can be increased, right? So what is the best way to cancel these elements? If we manage to add additional component, like if we have capacitor here and manage to add additional inductor to cancel the effect of this capacitor, we can extract the maximum power. Okay, so this is one of the advantages. That's why we are going to study or to use resonant converters in power electronics. They are very useful. There are a few disadvantages, of course, but there are also loads of advantages. Again, one of the main advantages is that we can extract the maximum power. Okay, if we try to draw the curve of the current, this current IR, let's say we're studying the current in the series resonant converters. So I want to look at the current here that is flowing within this circuit and see what happens if we increase or decrease the frequency, how the current behavior looks like. Okay, so if you try to draw the frequency versus the current, V input over R, okay, you'll find that the current curve will be something like this. So here at some point, what we call the resonant frequency, you will find that you can obtain the maximum current. If you increase the frequency at certain value, you will find that your circuit here, the series resonant converter circuit, it will act as inductive circuit. Okay, if you reduce the frequency, this will be a capacitive circuit. Okay, so if the frequency is larger than or greater than the resonant frequency, so this is inductive circuit. If the frequency is smaller than the resonant frequency, this is capacitive circuit. Okay, so this is the resonant frequency. Let's have a look at the current here, IR, and try to find the expression for this current from the series resonant circuit. IR is equal to how much? The input voltage, V input, over the impedance of this network, right? Of this circuit, the resistive plus capacitive plus inductive, right? So this will be R plus the capacitive impedance or reactance is equal to how much? 1 over J omega C plus J omega L. Try to make some simplification for this expression. This and this together, divide by J omega C, you will find that IR is equal to how much? V input over R plus here J omega C, and on the upper side is 1 minus omega squared times LC, right? So this is the value of the current. Now let's look at this current and see when this current can be the maximum value. This current can be the maximum value when this term is equal to 0, right? Because whatever the value of this term, so this will decrease the total current, because of V input over R plus any value, this will be definitely less than V input over R, right? So the maximum current occurs when this term equal to 0, and this term is equal to 0 when 1 minus omega square LC is equal to 0, and then this is equal to how much? Omega square LC is equal to 1, and from this we can say that omega is equal to 1 over LC under the root square. So 1 over the root square of LC. So this is omega. So this is the frequency that can obtain the maximum current, right? Which is what? Which is the resonant frequency. So that's why I will call this one what? Omega naught, right? Omega naught is the resonant frequency. F naught is equal to how much? 1 over 2 pi times LC. And this is the resonant frequency in hertz, and this with radian per second. Unit is radian per second. So we know why we need resonant converters. When the resonant converter or the resonant circuit can obtain the maximum current, right? When we have a resonant frequency, or when the equivalent impedance here is equal to how much? R only. Now when this is equal to 0, this term is equal to 0, but the capacitor and the inductor cancel each other, but there is capacitor and inductor. Okay, we don't remove the capacitor and inductor, but the behavior of the capacitor and the inductor, like they cancel each other, okay, as if we don't have any capacitor and inductor in the circuit. And this is the beauty in the resonant converters, because actually we have the capacitive side in the inductor and the capacitor in the transformers, for example, we have parasitic capacitance, right? So if we add additional circuit, we can cancel these, the effect of these capacitors. If we manage to add these circuits, we can cancel the effect of the parasitic elements, for example, and increase the power transfer. Okay, now let's go in depth and study some of the things like what we call the quality factor for the resonant circuits. Okay, what is the definition of the quality factor? The quality factor, or the Q factor, is defined as the characteristic impedance, which is the equivalent resistive impedance over the resistance. The characteristic impedance ZR by definition is equal to how much? L over C, which is the equivalent resistive impedance, and Q is equal to how much? ZR over R, right? ZR is how much? L over C, and this is divided by R, okay? Try to make some simplification for this Q. You'll find that Q is equal to how much? Multiply by omega naught. So we can say omega naught L over C over omega naught times R. Omega naught is equal to how much? 1 over the root square of LC. So we can say that omega naught times LC altogether times L over C, and this is divided by R because we substitute this omega naught by 1 over the root square of LC. So this is simply is equal to how much? C will go with C, L times L, this will be L, so this will be omega naught times L over R. And this is for what? For the series resonant circuit. Okay, so the quality factor for the series resonant circuit is equal to how much? Omega naught times L over R. Okay, omega naught times L over R, or 1 over omega naught R times C. So this is for series resonant circuits. For the parallel resonant circuits, the Q factor is different, is equal to how much? R over ZR, which is how much? R over omega naught L, which is omega naught times RC. For the parallel resonant circuit, we need to make sure that our capacitor and inductor act as what? As an open circuit. For the series resonant converters, we need to make sure that our capacitor and inductors act as a short circuit. Now, if you try to draw the curve of the current, you'll find that when the quality factor is high, you'll find that, let's say this is Q2 and this is Q1. In this case, Q2 is larger than Q1. So when the quality factor is large or high, then you'll find that the curve is narrower and we have the band of frequency is very small. So we can obtain the resonant frequency, but the amplitude, if we try to increase or decrease the frequency, will be very small. But if you try to decrease the quality factor, in case of series resonant converter, you'll find that the curve looks like this. Now, this quality factor issue, when we increase the quality factor, this can significantly increase the behavior of the filter within the resonant converter. So let's say, for example, you want to apply a very significant filter, okay, to allow a band frequency to pass and reject other frequencies. So what you need to do is to increase the quality factor. If you want to decrease the quality factor, then your filter, for example, will not reject the higher frequencies or the lower frequencies effectively. Now, this is when the input voltage is only a sine wave. Just imagine if we have the input source is not a sine wave source. Okay, let's say it's a square wave. What happens if the input voltage is square wave like this? So if we have sine wave on the input, this means what? Let's say this is a 50 hertz, or let's say it's a 50 hertz frequency. So the current versus frequency curve, it will be something like this. So this is the resonant frequency. The resonant frequency occurs at a certain point. Let's say, for example, the resonant frequency is 50 hertz. And if we increase the frequency, the curve will start decreasing like this. And if we try to decrease the frequency, the curve or the current will start decreasing this way. Now, if we have a square wave, then we have how many harmonics on the square wave? We have many harmonics. We have the first frequency, the fundamental frequency, the 50 hertz, for example, and we have the third harmonic, the 150. We have the fifth harmonic, which is how much? 250 hertz, right? And so on and so forth. We have the seventh harmonic, and so on. So we expect that here we have multi-peaks, right? One occurs at the third harmonic, and one at fifth harmonic, and then at seventh harmonic, and so on. The curve should be something like this. Why? Because the square wave here, the input is what? Is a square wave. Now the issue is for the resonant converter, when we have a large Q factor, you'll find that these peaks here are very small for many reasons. Number one, the third harmonic, fifth harmonic, and so on, by default they are smaller than the first harmonic. The peak of these harmonics are smaller than the fundamental frequency. And the resonant circuit, the combination here, the capacitor and the inductor, will act as a filter. So this filter will make sure that we have what? This filter will try to act as a filter and cancel these harmonics here. Okay, so the amplitude of this harmonic will be very small because we have filter. Now the question is, now we have another question. Now let's say, for example, you have this curve, okay, and you have the option to increase or decrease the current here, right? So if you operate at this frequency, the current will be smaller. So you'll be able to control the current, right? If you operate at this point, also you'll be able to control the current. If you don't care about the frequency, by changing the frequency, you can change the current. That's very good. Now the question is, should we go for the frequency that is larger than the resonant frequency, or going to the frequency that is smaller than the resonant frequency? Which one is better to do? To increase the frequency or to decrease the frequency? In terms of the amplitude of the current, there is no problem. Both should give the same value, okay? But why we prefer to go here on this side? Because here we have higher frequency. When you increase the frequency, you will increase the value of the third harmonic, the fifth harmonic, and so on. And third, fifth, seventh will be far away from the fundamental frequency, so you'll be able to cancel this one by using a smaller value for the filter. You'll not be able to use large filter at this moment, right? So we always prefer to go to higher frequencies, because if we go to higher frequency, you'll find that the third harmonic will be even larger, and your resonant circuit will be able to cancel this harmonic easily.